video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
Later. Next presentation is Basic Concrete Forensic Analysis, Rick Edelson. He's past president of the ICRI, and he's a partner of Tadger Cohen, Edelson, and Associates out of Silver Spring, Maryland. Please welcome him now. And
Thank you. Thank you. I'm going to try to pick up the pace a little bit here. We have well, if the computer's going to go forward, maybe it's been sitting there so long. Okay, concrete forensic analysis. It's got a couple other names, but we're talking now the beginnings, the very basic things of what you do before we do the repair. Okay, it's got a couple other names to it: project diagnosis, evaluation. I'm going to go a little bit quickly. By the way, I've got about 70 slides, so you're going to have to keep up with me, and I got 30 minutes to talk about them, so I'm going to keep on going pretty quickly. We talk about what we're going to do. What's the purpose of this presentation? Okay, what do we do to diagnose concrete deterioration? Okay, how do we go about doing it? Very important in a couple of steps. What do we look for? This is important. We have to know what we're going to be doing. Okay, and what are our goals? If you don't know your goals, you don't know where you're going to be going. All right, so what are our primary goals? It's to determine the source of the problem, because here is the key. Without fixing the source, the problem is not solved, and the repair, I say will not work, but it may not work. Okay, this is key. If you don't solve this, you're not going to solve your repair. And what's our tools? Let's get into a couple things that we have. Number one tool is you. It's your noggin right here. Okay, you've got to be thinking about what you're talking about to analyze the problem. I mean, here the guy thinks this is a drafting error down here at the bottom. Okay, well, maybe not. And key to your tools is your client. Never stop listening to him. Okay, he's here. You're coming here on maybe a brief occasion. You have a small window in time. You're taking a look at this project, but he lives with this project. Listen to him. Listen to what he talks about. Understand what he says. All right, let's get into a couple of tools. The primary tool for listening for deteriorated concrete is right here. It's the chain drag. Okay, it's not very sophisticated. You can get it at Home Depot for a couple of bucks. You can see over here is another type of chain drag. This is actually an ASTM standard. We now have an ASTM standard for doing a chain drag. So you can make it. This one's made with a bar and a couple of chains, but we happen to find that this one works very nicely. Now, you'll notice that he's got a very nice big one, but all of you engineers are dressed in suits, so every once in a while, you pull up your little one, okay? And you can carry this along with you all day long and never get tired. Now, what does it sound like? It's a little hard to do it in here because I don't have good solid concrete and I don't have hollow. But you hear the hollow sound, okay? That's what you're listening for. Okay, so as you drag the chain across the floor, you're listening for that hollow sound. There's a couple other devices. There's a hammer. Okay, I happen to like a mason's hammer. All right, it's got a nice sharp point on the end. Sometimes you want to take out a little bit of concrete. But here also, you can tap it on the concrete and take a listen to it. There's a couple of sophisticated devices. One of our exhibitors out here has a very nice device that you can roll along the concrete to take a look for it. But we're looking for delaminated concrete. A couple other tools that you have to have. Gotta have a flashlight. Okay? If you don't have a good solid flashlight to see what you're doing, oftentimes you're in a garage that's as dark as here. Okay? Good flashlight, you can see what you're doing. But of course, you're always good engineers. You're nice and dressed and very cute and all that kind of stuff. You carry your little flashlight. Okay? I can't tell you how many times I go to a building and they say, oh, by the way, they want to see this. So I carry my little flashlight with me. It's kind of nice to do some of these little things. Okay? A couple of other tools. The packometer. Where's the reinforcing? What's the cover of the reinforcing? You can see a type of packometer. Packometer is only a metal detector. Okay? We're just looking for where the rebar is located. But with this device, you can also find how deep it is in the concrete, assuming you know what size. There are many kinds. One of our exhibitors out here has another type. Our guys happen to like this one. This is a device that has the meter right next to it, and you can do it overhead, you can do it down, and you can see everything all at one time. Okay? So the tachometer is an extremely valuable tool. A couple others. How much corrosion is really going on inside of this concrete that has not yet delaminated? We have a half-cell study. Corrosion is only a battery operation. So if we put a big voltmeter on it, we can read the voltage. Okay, well, once we read the voltage, we can get contour signs around the rebar where you're most active. So we can get a prediction of the future. Okay, it hasn't delaminated today, but maybe it will delaminate in the future. This is also one of our exhibitors here, has this type of device, as well as there's others. All right, a couple other slick tools. This is relatively new, ground penetrating radar, GPR. Okay, GPR is pretty slick. We can find voids inside of concrete. We can find rebar. We can find post-tension. This is the device. You can see the operator. Here's the sensor down here. They get a radar screen, but it's kind of hard for me to read it. However, what I get out of it, this is a post-tension beam that was having some problems. Okay, with the GPR, we were successful finding every single tie in the beam. And of course, we could find the rebar is this red line, or I'm sorry, the PT cables are the red line. And guess where that's supposed to be? It's supposed to be down here, because right here is where the column that's above this transfer girder is being supported. And here's the low point. Well, why did we have a problem? Because right there's the PT. Okay, so with GPR, we were quite successful in finding what was going on. We can also tell the difference between rebar and PT. Okay, in this particular graph, and I can't really read the graph, but what they tell me is there's the tendon and here's the rebar. So with GPR, it's a slick device. Okay, a couple other things. Post-tension. If you get into post-tension, we have to do some excavations just to find the cables. And now how much stress is actually on the cable? What we used to have to do is we'd have to cut the bar, cut the PT, put a locking device on it, and pull it. I can tell you how much is there. Okay. A couple new devices. This slide is courtesy of Halsall, the people that provide this. If we pull on the cable, if I can find it, grab it, and pull on it, I can tell you how much tension is on there. If I drive a screwdriver through the strands, if it's a multi-strand cable, I can tell you is it stressed or is it not stressed. Well, driving a screwdriver through PT cable all day long, you know, your arms get kind of tired. A slick device is called a slide hammer. We're just sliding against the screwdriver, and you can see right here, we're trying to separate the individual strands. So this is a time saver and a muscle saver. Here's the device that they can pull on the PT cable, and depending on how much it deflects, it can be correlated to how much force is in the PT cable. Okay, so a couple of new devices. All right, let's get into the condition survey. We've got the tools. Now what? Problems have to be discovered. All right, there's a couple of guides. Okay, for those of you getting into it, now you don't need to write this down. I put in the back of the room as you go out a whole list of what you see here on the screen. Okay, but we've been doing this for quite a long time, so there's a lot of guides. ACI, of course, has been around the longest, so they've got quite a few guides. ICRI, we're coming up with the evaluation of post-tension structures this year. This is an excellent guide. It's going to be about 50 pages long, and it's got a lot of things in it. So if you get into PT, an excellent guide. Okay, and it keeps on going. There's some more. More Ashto, the Corps of Engineers, Canada has some guides, and of course, our past president, his book from Peter Emmons. It's also an excellent book for basics. Not only condition surveys, but getting into the basics of repair. All right, so what are we looking for? All right, a couple of things. I've got 4 different slides here with several different problems. Okay, but what are the sources of the problems? Each one is different. The repair in each scenario is different. Have to know what we're going to be looking for. Okay, but in that, we have to get some documentation. I go back to the chain drags again. Here I can see the ASTM number on the chain drag. But what's the result of it? We have all the delaminations. Now, in our office, we usually prepare a plan. On this particular plan, you can see all of the delaminations throughout that entire structure. Okay, but what good is it? We need to know how much. Here's a little bit of a trick. What we do is we add up the quantity per bay. Okay, Okay, so for instance, in this bay, I've got 285 square feet of delaminations. Some people may mark it on each individual one, but we do it adding it up per bay. Okay? Now we can add all of that up, and we have a matrix of all of our findings. This is just a simple spreadsheet on some fictitious garage, but you can see I've got square footage, linear footage, and each of all the different items that we have found. Added up by level, by floor, whichever way you want to go, and here's the result that you can now present to your owner. This is a little hard to see, but I've got all of the findings. I have estimated unit costs, total costs, and here's the bottom line, the cost of doing that project. So now I've presented to the owner, I've not only found all the problems, I've presented to him a cost. Okay. But what caused all this deterioration? All right, is it settlement? Is it deflection? Okay, maybe it's expansion, contraction. We've got corrosion, big thing. I'm going to talk about that in a little bit. Water, maybe it's just simple water getting in. Okay, or is it construction related from the original construction? We have all of these things to be thinking about. Okay, is it some chemical or deleterious material that's inside of the concrete? Every one of them is a different source and may have a different repair. You have got to know which one it is. All right, so let's go back to that slide. What were the symptoms? On this particular one, it happened to be from flexural cracking. The study found that the rebar was 4 inches below the surface. It wasn't up at the top. It was supposed to be designed with 3/4 inch cover. Okay? It was too far down. On this particular one, we have severe chloride ingression. Okay? This was so bad that this structure was recommended for removal. Down here, our typical spalling. Okay? This spalling, the source of this was corrosion. Totally different than this problem. So if you use the same repair for these two, you've got some real problems. Okay, you may not have solved those. And then this particular one was just a straight crack, and we were getting leakage through simple cracks. I happen to like this slide because this stalactite here is about 4 feet long. It's under the National Gallery in Washington. Okay, diagnose the symptoms. Okay, of course you got your visual. You got to be looking at what you're seeing. Okay, we could be looking at spalling, or we're looking at scaling. Okay, which one are we actually looking at? That's with your eyes. Do we have broken PT cables? Do we have crack patterns? Each different crack pattern may have a different source in the problem. You saw that earlier slide of the flexural cracks. I'll talk some more about different other types of cracks. But each different crack pattern, different problem, and you've got to know which one it is. Okay? Are they spider web? Are they diagonal? Are they straight? Okay? Are they alligator pattern? Every one is different, and the source is different for each of those. Okay, diagnose the symptoms a little bit more. Structural analysis. Okay, that one with the flexural analysis, bars were down too far, we had to do a computer analysis on it. Okay, some computations in order to determine, yeah, it's actually overstressed. Maybe it was okay, maybe it's not. Of course, you have the old hand computations. A little bit more. Laboratory analysis. Maybe it's something inside the concrete. I'll show a little bit more on lab analysis in a moment, but it's a key piece. Don't forget your lab analysis. I mean, sometimes maybe visual's enough, but lab analysis is very important. You've got petrographic, which is your microscopic analysis. Concrete quality. How are you going to know about air entrainment? That's a key piece. Maybe it's a freeze-thaw problem. You've got alkali-silica reaction. Okay, I'll show you a slide of ASR. ASR sometimes looks like something else. If you didn't do the lab analysis, you wouldn't know which one it is. Could be carbonation problem. Okay, could be a chloride problem. Okay, again, these are all laboratory analysis. Maybe it's chemicals. Maybe it's a cement content. Okay, there's all different things that the lab has to look at. All right. This is a slide of a particular core, and in this particular slide, it shows that the crack is going through the aggregate. Now, there's a very different problem if the crack were going around the aggregate. Maybe the source of the cracking is different. Okay? But if I hadn't looked at it under the microscope, I wouldn't know what that crack is doing. Also, if I look from the top surface, is the crack full depth or is it partial? This particular one tells me it's going full depth. Okay, so again, it's the laboratory analysis. All right, now let's talk about corrosion. I'm going to slow down just a brief amount on corrosion because it's key to everything that we do. All right, and I'm going to start with this premise. Okay, and the premise is that steel and concrete cannot and will not rust. Almost ever. Okay, unless one of two things happen. Carbonation and chloride. If one or both happen, we're almost certainly going to have corrosion. If neither one happens, most likely you're not going to have corrosion. And here's the key to it. Okay, with normal concrete, we build a passive oxide layer around the reinforcing steel. Normal concrete has a high pH. It's about 13. And at that pH, this passive layer will stay up and protect the reinforcing, okay, unless one of those two things happen. Now, in the carbonation, it's a chemical reaction between carbon dioxide in the atmosphere and the concrete, forms an acid, and the acid lowers the pH. Okay, once that pH lowers, gets down about 11, we're going to have corrosion. I'll show you a slide of that in a moment. The other, of course, is chlorides. Chlorides does two things. Chlorides have a pH of about 7. Again, that pH of 13 or so for the concrete, it's trying to neutralize it and lower it. So that's number one. Number two, it's putting an electrolyte inside of the concrete. And it's allowing the flow of electrons to go across between the anode and the cathode. Now, I'm not going to get deep into what the corrosion process is and the flow of electrons and all of that. Okay, but it's key for the carbonation and the chlorides. All right, let's take a look a little bit at that carbonation issue. Okay, 4 slides here. This is a core of concrete, and it has phenolphthalein sprayed onto it. And phenolphthalein will turn pink at the high pH. You can see the carbonation on this particular core is only up at the very top. This core, you've got deep carbonation. Down here is the uncarbonated, and here's your low pH concrete. If there's a bar in here, I can guarantee you you're subject to corrosion. And you can see the sample here. This is uncarbonated, here it's carbonated, and here you're having a rusting rebar. Okay? If you're in the field and you can't send it to a lab, well, you can still check. Here's the worker spraying phenolphthalein on the sample where the concrete has been removed. Okay, so we can field check if there's a carbonation issue. Okay, let's go back to that slide of the crack again. Okay, notice where the pink is. Okay, notice that the pink has gone all the way down into the core. Why? You've got a crack here. Okay, so not only did that slide show us a potential source of the crack because of the way the crack goes through the aggregate, but it also shows carbonation is an issue. Okay, so if we have cracked concrete and I have a rebar right there, guess what? Okay, we have a potential for corrosion. Okay, so again, our lab analysis is double checking what we see in the field. All right, let's talk about chlorides for a moment. All right, ACI puts a threshold to initiate corrosion. We don't need to get into the pounds and all this kind of stuff. Okay, the important piece is there's a threshold to initiate it, and we have 2 primary sources for it. Okay, in the east, such as this part of the country, we have our road salts. Okay, we throw salt on the street in the wintertime, it grabs onto the snow packs to the bottom of the car drives into a garage, the snow melts, and now we have salt water onto the garage. Okay, of course, in the old days, we were allowed to put calcium chloride. Okay, and it was actually written in the ACI code until about 1963 or so, or about 1972 or so, that it said in the ACI code, calcium chloride does not cause corrosion. And guess what? We were wrong. Okay, we finally learned that calcium chloride, when it gets wet, does cause corrosion. But if you have the old 2% cal that we were allowed, is really much greater than, that's about 1.25, here it is. It's 1.25% by weight of cement. And here's your level to initiate corrosion, or the allowed, and this is the actual level. Okay, so you can see it's many times more than the threshold to initiate corrosion. All right, let's talk about the corrosion mechanism. How does it actually work? All right, we have some concrete, good solid concrete, and here's your reinforcing steel with your passive layer. Sometimes there's a few flaws in the passive layer, but you can see the chlorides start coming from the top. They progress down and they come down to the rebar. Eventually they get down to the rebar. Okay, the corrosion starts, and now we have the rust product. We have cracking. We have more chlorides. Okay, but why is all this so detrimental? And here's the key piece. Okay, corrosion, when it occurs, the steel expands 4 to 10 times its original size. It's the old story, you put water into a glass jar, freeze the water, as it turns to ice, we all know the ice breaks the jar. Well, if you put a rebar close to the top surface, allow it to expand, and guess what? Here it cracks the concrete. And as it expands more, it cracks more, and it just snowballs. But that's the reason why we have the spalls, because the rust is expanding. It's the only reason. All right, what's the progression of a spall? Okay, we have a little bit of outward force, It gets bigger and bigger. If you take a look at it at the end, as the rust goes around, it creates a V-shaped spall at each rebar. You put multiple rebars together, and they all get together. And each of the V's come together, and now we have a big spall. And this is what we're looking for as the symptom of the problem. The problem is not the spall. The problem is the corrosion of the reinforcing steel. And the source of the problem is chloride or carbonation. And that's what we have to treat. We have to treat the symptom. If you simply treat the spall, you may not be successful. Okay? A couple more pictures of the spalling. I love this one of a balcony. I can count every single rebar going across that balcony. Okay? Some of them get pretty nasty. Here's a column and a couple of rebars. This was a very heavy number 11 bar that was at the edge of a slab, or I think a number 8 bar at the edge of a slab. Here's a column, and they couldn't get the two in the same plane. Okay, so they put the heavy bar, the horizontal bar, on the outside of the column steel. Now it had no cover, and it got even worse. Of course, this building was built in the wintertime, and it had 2% cal. Okay, 2% cal plus low cover, and guess what? Here we have it. Okay, this is what we usually see in our garages, and this one is on the bottom. Okay, here we had the chlorides going all the way through the concrete, coming down to the rebar. If that piece of concrete falls and hits you, I can guarantee that thing weighs probably 10 to 15 pounds. So someone's going to get hurt. This, when you get down into this range, this can be dangerous. Okay, in the chlorides, when we do a study, you always take cores and do chlorides top and bottom. Okay, now you can also do it multiple through the core, but if you can see, there's a variation. Okay, if there's a variation like this, we've got high chlorides from road salts, and maybe we've got chlorides from base concrete. Okay, so when you do a progression across the core, you can tell what you have. Okay, let's get into some cracking. All right, what kind of cracking do we have? Full depth versus partial depth. Big difference. In that slide you saw of the bottom spalling, we had full depth cracking. We allowed the chlorides to get all the way down to the bottom very quickly. If it were partial depth, maybe that wouldn't happen. Key question, is it moving or non-moving? Okay? If you can answer that, you may be successful in how you seal it. If you can't answer it and you put the wrong material in it and it moves, we're going to crack that material. Okay? You have to know the answer to that question. Wide versus narrow. Some materials can go into a wide joint, some can only go into a narrow joint. Two different solutions. Okay? Is it stress related, or is it moving versus shrinkage? You've got to answer this question in order to be successful in a crack repair. Okay? Of course, full depth cracks. This is a little bit larger of that previous slide where I have the 4-foot long stalactite. And then you can see on this one, you've got the lime leaching out of the concrete. I mean, that is lime that comes out of the concrete. And if it hits a car inside of a garage, it's a written guarantee it's going to take the finish off of a car. So you need to solve that problem. All right, let's talk about the restraint. All right, in concrete, if you pour concrete between two rigid, immovable objects, initially if you break it and allow it to be free from the immovable objects, it shrinks. All concrete shrinks. Yeah, there's shrinkage compensating and all that other stuff. All concrete shrinks, as Alex had said earlier. And we get a gap at both ends. Now if I tie one end and allow it to shrink, it's going to shrink at the other end. Okay, but if I tie both ends and it wants to shrink, something's got to give, and it's usually the concrete. Okay, and here's what happens. All right, now this is an easy example, but if you also imagine a huge structure, a big plate, all right, and you look at the center of the plate compared to the outside maybe that part's not moving, but the inside is moving. Okay, you can get this type of a crack simply in a big structure, because the outside didn't move relative to the inside. So you can have restrained cracks even in a slab that may appear to be unrestrained. Okay, and what do they look like? Restraint cracks are usually full depth, and they're usually straight lines. Okay, in a balcony, they're coming straight across, and you can see, even though this is the edge of the balcony, they're still coming across. Well, here's a very, very rigid column. In this building, they had huge columns, and the columns were immovable. And right between each of the columns, I got horizontal cracks. So this is a restraint type of cracking. Plastic shrinkage. Okay, let's take a look at the type of plastic shrinkage. Usually they're partial depth, they're narrow, and they're usually non-moving. Going back to that previous slide, in this balcony, as this balcony heats and cools, you're going to get thermal movement. You're going to be moving each one of those cracks. Okay, so it's key to the repair of this crack. Now this is a garage. As the cars drive across the garage, it's going to be flexing up and down. Okay, so in reality, that's a moving crack, even though it's in a garage that has a uniform temperature. Now these are often at the very top surface, and they usually won't move. But the pattern is totally different. Okay, here you have your alligator skin pattern. This is the plastic drying, and you get these little cracks along the top surface. Okay. Here's that alkali silica reaction that I showed you or talked about earlier. Take a look at that crack pattern. That's very similar to one of these crack patterns. Okay, but the source is very different. It's alkali silica reaction. I'm not going to go totally into ASR, but essentially we get a gel that expands inside of the concrete as the concrete gets wet, and it breaks the concrete apart. Okay, this is another picture of it. And again, if you didn't do the testing for ASR, you may not know the source of those two cracks. Okay, the stress cracking. As I talked earlier, this is actually a flexural crack. This was due to the rebar being in the wrong place. And here's a flexural crack coming through a repair. Now, why did that come through the repair? We had all this brand new nice concrete on it. Well, it's simple. Remember that moving crack? This garage floor moved. And as it moved, the cracks mirrored from the base concrete right back up into the patch. Okay, so again, you have to be thinking about your cracks. Are your cracks moving or non-moving? You may have to treat this differently. Stress cracking. All right, back to that earlier girder that I had showed you. We had some other problems. That's getting a little hard to see on this slide. But right here, you can see there's a distance of 12 inches where they forgot the ties. It must have been because of the shape change. But right here, I have a diagonal crack. And what's that diagonal crack? That's a shear crack. Okay, we had the same thing going across here. Here's a large space without the ties. Again, it's a little hard to see in the slide from where you are, but there's diagonal cracks. So with the GPR, with the layout of all of the ties, we were successful in determining the source of what this problem is. Okay, here's that moving crack, okay, with a misdiagnosis. All right. This is an epoxy material, a rigid material, put into a moving crack. I'm not here to say epoxy is a bad material. It's an excellent material, okay, in the right place. But because this crack is moving, maybe we should have thought of something different, okay? Maybe it should have been a flexible material, something that could absorb that movement and move along with that crack. Okay? Every one of them is now leaking. Sometimes you'll get in an epoxy crack, you'll get a new crack right here, right along the existing epoxy, okay? Because that epoxy is stronger than the concrete, and sometimes its bond is better than the concrete itself, okay? But this is a misdiagnosis on a crack, okay? Movement, got to be thinking about your movement. This happens to be a post-tension structure. In this one, we have a large post-tension slab, concrete wall, and a very rigid column, and these huge cracks in the column. Well, why did that one crack? That's not a compression failure. In this one, the slab moved in this direction and pulled all the columns. Now, I only show one of the columns. It just so happened every single column was having that same crack pattern. That was over towards this end of the building. On this particular one, this was a slide bearing. It was an expansion joint. And you have a post-tension girder on this side. Well, due to water, salts, and corrosion of the slide bearing froze. And they tried to repair this thing multiple times. And this is patch after patch. And finally, we took a look closely at the bearing itself. Okay, we freed the bearing. Now the patch works fine. Okay, again, it's the source of the problem. Okay, go back to the source. Okay, that restraint crack I talked about earlier. This happens to be a precast panel. And the precast panel has a very nice, stiff, welded connection here at this end. Well, it also happens to have the same connection at the other end. Well, that panel is now welded and solid at both ends. It can't move. Well, remember, concrete's got to shrink. Okay? Or even with thermal movement, it's got to expand and contract. So now we have a nice crack right here at the edge of the support. Okay? And again, why is this happening? Got to understand why. Similar crack. This happens to be a precast beam that moved this way. Again, it didn't move very well at the slide bearing, and now we have a crack right here. Same structure with a similar crack. Again, it's a little hard to see. You can see the crack right here at the edge. Now, why did this one crack right here? Well, this is a long precast girder, and I got Deflection of the girder. Well, if you look at the deflection of the girder, you have rotation at the very edge. Well, on the rotation, we got high bearing stresses right here, right at the edge. And that high bearing stress caused this crack. Okay? Same structure, similar cracks, different problem. Okay? The repair of this one versus the repair of the previous one, this one, they may be different. Okay? I don't want to get into what the actual repair is, but you've got to go onto the source. Okay, scaling. I love this slide. This is a great slide. Okay, this happens to be by the front door of my office. Okay, and the poor guy that did this did it on a Saturday all day. We had the door closed. Everybody had to use the back door. And I watched him pour the concrete. I was just watching from my window. And all of a sudden, somewhere about mid-afternoon, just as he was finishing his concrete, it poured like hell. I mean, a cloud burst came down, and the guy was not protected. Okay, he went back there and he finished and he worked on it, and it looked okay at first. Okay, this is 5 years later, and this is now 10 years later, and we have a very nice exposed aggregate finish on our sidewalk. Okay, now if I were to do petrographic analysis, I could see the high water cement ratio at the top surface, and I could see a progression of water cement ratio as you go down through the concrete. So yes, I can tell that. Now I happen to know that exactly what happened here. Okay, but this problem could be caused by other things. Okay, maybe it's just bad concrete, maybe it's overfinishing. But if you do your lab analysis, you can come exactly with the source of that problem. Okay, now with the lab analysis, I could also tell how deep that goes. All right, now if I put a simple repair material on top of that, as Alex had said earlier, you have to treat your whole structure. All right, if I put a repair material on top of that, that repair material is going to come apart. Why? Not because the repair material is bad, but because that concrete right there is bad, okay? And that's going to come apart. So you have to know your source. If you know what the source of that problem is, you can probably fix that. All right. This is a slide I like to show to condominiums when I argue why carpet is bad on the top surface of balconies. And in this slide, this is really the slide that I like to use, you see the 4 balconies. Now this particular photo was taken 24 hours after it stopped raining. Okay. These 3 balconies have no carpet, and this one does. And you can see coming out of the edge of the balcony, the water is still oozing out. Okay. Water is being forced into that concrete. Now, if spalling is an issue, and I don't remember if it's an issue here, but if spalling is an issue, that guy's going to have more of a problem. Okay. You can see from the top of another balcony a little bit of drainage towards the rear, but the green carpet is holding all of that water in. Okay. So these are the 2 slides that I use to show why carpet can be bad. All right, post-tension. A couple of examples of finding post-tension problems. This is the old one where it pops out. You know, as a post-tension cable breaks, it's like a rubber band and it closes in on itself, and sometimes it'll come out of the bottom of the concrete. You can often see it on the top surface. Here you're just seeing the gray sheathing, and on this slide you're seeing the broken cables. Okay, so each one may be a different problem. You need to investigate it. Right, coming also from the bottom, some other telltale signs. You've got the grease. This is one that's been opened up. You have severe corrosion. And another one where you got a little corrosion and a little bit of grease. Again, you need to know the source. And here's the key piece. This is the last slide. If you know the answer to this question, you will most likely have a successful repair. If you don't know the answer to that question, I can guarantee you have a high probability of a problem with your repair. You must know that problem, the answer to that question. And if you're successful, we'll never get to this. And I thank you for your time.